What's up, everybody? Welcome back to the channel. I'm Phil. That's Sam.
Hey, guys.
For Bars and Barbells as a team, we've been getting a little bit of astronomy-based content on our channel. We do reactions to music, we do sports, we do military-based stuff, we do history, and we sprinkled in a little bit of astronomy in there as well.
Yeah, we've been doing a little bit more of that more recently.
Yeah, and you've really enjoyed it, right?
Yeah, I think it's really cool to learn about what's out there. I feel like it's so much of it is unknown, right?
We were blown away by the size differential in the last video that we
one
did.
was crazy.
So crazy. We couldn't believe how things just kept getting bigger and bigger.
You can't even wrap
bigger.
your head around how big it really is, though. It's
and
crazy.
that actually wasn't the most recent one that we did. The most recent one that we did was about the Milky Way.
Oh, yes, the
really
Spaceman
cool
one.
Yeah, that was super cool.
Really cool. And the graphics in that were insane. Highly
well
recommend
done.
going to watch that if you haven't.
Yeah, not a lot of people caught that one, so you guys should go back and watch that. That was really, really cool. Anyways, we're coming to this one in light of the topic of astronomy and into a general relativity, and this is Albert Einstein's domain. I think this is like the addition to Isaac Newton's theory, and I don't really know. I've heard the term general relativity, and I've I think probably heard about it maybe in university or something like that. It's been a while since I've been in university. But it's clearly something I'm not comfortable speaking about in any educated manner. And that's why we're going to do this video here.
Yeah, I can't say I really know anything about it. I've heard of the term used before, but I don't. All I know, it has something to do with gravity, and that's it. So.
Gravity, space, time.
Yeah.
But really influential in how we view the universe, and I think there's even stuff that we use today that are based around this idea. So anyways, guys, if you have insights on this stuff, we love learning, so drop it down low in the comments. Hit the subscribe button. It's your first time on the channel. We do all different kinds of content, and that like button, like Sam said. All right, let's find out if we're gonna have any ability to understand what's going on this one on general relativity.
When Einstein first published the special theory of relativity in 1905, he was either vehemently ridiculed or ignored. People thought it was just too weird and radical to be real. This guy is not even a working scientist. He's just a patent clerk, some said. How dare he challenge the greatest scientist that ever lived, Isaac Newton, whose theories have been proven to be correct for hundreds of years. Some politicians even insulted his religious heritage and called it Jewish science, a way to subvert traditional culture and thinking. How did Einstein feel about this? Well, he wasn't satisfied with his theory either. He was unhappy because the theory only applied to observers moving in a straight line at a constant speed. The theory did not apply if gravity was present or if the observer was accelerating. Einstein was known, however, to have a very vivid imagination.
I would say so.
One day, as legend has it, while observing a window washer on a ladder near his patent office, he had one of his famous thought experiments that would go on to change the course of scientific history. He imagined what would happen if the worker were to fall, but he didn't think of it the same way you and I would think of it. What was his thought experiment, and how did it lead to perhaps the greatest single scientific theory of the past 100 years? That's coming up right now.
So I guess we got Arvin Ash that's going to explain this complex question to us. Pretty cool. I mean, I'm interested to see where we're going to go with this now, because, the fact that he saw his window washer and that kind of stoked the concept in his brain.
Sometimes people get like the greatest ideas with like the most simple origins.
It's crazy to me, though. Like, I never heard that before, that this potentially blossomed, the seed was planted from his window washer. That's crazy to me.
While watching the window washer on a ladder, Einstein thought about what would happen if the window washer fell. For most people, imagining this would just conjure up disturbing images of the poor guy landing on the ground below, and the story would not have a happy ending. Einstein thought about it differently. He put himself in the window washer's perspective and imagined not what would happen when he met the ground, but what he would experience as he was falling. What he realized was that if he was falling, gravity would be the only force acting on him. He would be accelerating towards the ground, but since the ground would not be pushing up against his body, he would feel no weight. With no wind resistance, he would be in free fall. and this would be no different than being weightless in space. In a way, gravity and acceleration were different ways to describe the same thing. This is where Einstein had a huge insight. The way to connect gravity with the theory of relativity was through the idea of acceleration, since the two are equivalent. Einstein imagined being in a room with no windows. And if the room had a bathroom scale handy, what would happen if you stepped on the scale? Well, if anywhere stationary on Earth, you would weigh 80 kilograms, or whatever your weight is. Now he imagined being in the same room in space. Now what if the room was on a spaceship that was accelerating in an upward direction at 9.8 meters per second, which happens to be the exact same as the gravitational acceleration on Earth. What would happen when he stepped on the scale then? Well, the scale would read 80 kilograms, just like it did on Earth. The acceleration on the spaceship would appear to him inside the room as being indistinguishable from being stationary on Earth. If he didn't know he was on a spaceship, he could just as well presume he was on Earth. There would be no way to tell the difference. Or would there? Einstein thought about this and asked himself if there was a way to tell the difference. He imagined what would happen if he took a flashlight or a laser beam and pointed it from one side of the room to the other as the spaceship was accelerating upwards. If he had a sensitive measuring instrument, he could measure the height of the light on the other side of the room. He realized that the height he would find on the other side of the room would be slightly lower than the source of the light. Why? Because the floor of the room would be rushing upwards at ever faster speeds as the light was propagating across the room. Since the room was accelerating upwards at 9.8 meters per second, the light beam would appear to curve downward. However, if you were on Earth and you measured the two heights, you may think that there should be no difference. The light should go straight to the other side of the room. This appears to be common sense. But Einstein thought this can't be because it would violate the principle of equivalence. Acceleration of the room on a spaceship should be no different than the room under the influence of gravity on Earth. He realized that this meant light must bend in the presence of a gravitational field. But how could this be? Because light always takes the shortest path between 2 points. It should be going straight. Then he realized, wait a minute, maybe the light is taking the shortest path between 2 points. Maybe the shortest path is not a straight line. He imagined the curved surface of the Earth, the shortest path between...
Okay, how do you think about that?
I could never even imagine those thoughts going, like that order of thoughts going through my head.
Like, that's so wild to me that he was thinking about this stuff. I mean, it's one thing to think about the window washer idea, but then he thinks about the rocket being in space and
the curvature of light.
Yeah, I mean, that's crazy. I mean, it's very, very cool. And this guy's doing a fantastic job explaining this, following this somewhat so far. And, it makes sense to a degree. I think we're probably getting into a more complicated part of this, of the bending of the light aspect.
Yeah.
But that, the equivalence factor and the way you're seeing him reason it out is really, really cool to see how his mind was working through the problems to decipher the solution. And they're explaining it fantastically in the video.
I think the cool thing is that he looks at it in like a step-by-step process, right? So like, if this, then what this? What about this? If this, then what about this, right? And it's like he's working through it like, as you would with any problem that's much simpler, but he's just doing it on a much more complicated scale.
Yeah. Much more complicated.
Yeah.
Taking the shortest path between 2 points. Maybe the shortest path is not a straight line. He imagined the curved surface of the Earth. The shortest path between any two distant points on Earth, if you're restricted to the surface of the Earth, is never a straight line because you have to traverse the curvature of Earth. So the shortest path is always curved. So maybe gravity somehow causes a curvature of space itself. He hypothesized that in space, perhaps a straight line is not the shortest path between 2 points, and that perhaps in the presence of mass and energy, space somehow becomes curved, so that the shortest path the light can take is a curved path. This was the key insight that Einstein had about gravity. But in order to express this mathematically, it required very complicated mathematics that even a genius like Einstein could not easily figure out. He contacted an old buddy of his from college days, mathematician Marcel Grossman. Grossman had just finished his PhD dissertation on the topic of, wouldn't you know it, the geometry of curved space is called Riemannian geometry. With his help, Einstein figured out the mathematics of curved spacetime, and this curved geometry is really the basis of general relativity.
Wow.
Now you have to realize how different this was than the status quo of the time, which was Newtonian space and time, which presumed that time was fixed, space was fixed, and gravity was a mysterious force that could act at a distance from one massive object to another without touching it. In this model, gravity did not affect the underlying space and time, but acted within it. Einstein's theory was now that gravity was not a force between massive objects, but something that emerges from the interaction of space and massive objects. John Wheeler would later summarize the theory in 12 short words. Space-time tells matter how to move, and matter tells space-time how to curve. That's it. That's general relativity in a nutshell. And orbits of planets could now be explained not by some mysterious force that acts at a distance, but rather an interaction that takes place locally with mass or energy and the space around it. And this can be visually represented by the kind of graphic you see here to show how massive objects like planets form orbits around other massive objects. It's important to note that the trampoline analogy you normally see on TV shows and YouTube videos like this is a 2D plane used for visualization purposes only. The interaction occurs obviously in 3 dimensions, not just 2. It looks more like this graphic. Now this is much more difficult to visualize and animate, so it's typically not used, but it is more accurate. However, in order for this theory to really be taken seriously, it had to make a prediction that could be tested, and that prediction could not be explained in any other way. This test came in the form of Mercury. Mercury's orbit had been a mystery for decades because it was unusual. All planets orbited the sun in an ellipse. The planet closest to the sun, Mercury, also orbited in an ellipse, but it did something weird. It had something called a precession. What this means is that its ellipse never closes. The point of the orbit that was farthest from the sun advances a little bit every time Mercury goes around the sun. It's as if the ellipse itself is orbiting the sun. No one could ever figure this out using Newton's equations. When Einstein applied his new curved space theory to this orbit, the new theory predicted exactly the precession that Mercury actually has. Finally, a theory perfectly matched the observation, which had been a mystery for decades. You can only imagine how Einstein felt when he figured this out. There was a time when Einstein was the only person in the world who realized that the universe actually works this way. But
that's wild, because like, imagine being Einstein and
the only person.
You've come to this conclusion and nobody else understands what you're saying. You would think you were going crazy.
You can't really explain it to anybody because it's so above, like over their head.
Yeah, but even like psychologically, I can only imagine what that would feel like, because you understand something that nobody else does. And so part of you probably thinks, well, or gets frustrated. Why can't anybody else understand this?
Also, part of it might second guess yourself and be like,
exactly.
Am I crazy?
That's what I was going to say, is the other part is, well, maybe it's just, this isn't true. Maybe, but then you go to the math.
Because you don't have anybody to like back it up or validate it.
Right. That's why he went to the math, though.
Yeah.
To do the equations to find the definitive answer. Right. And that was a really cool example there, the orbit of Mercury and the curvature of space, and seeing how that, was explained was really cool. And I never knew that about Mercury.
I didn't know that either.
That it had, I had heard something about the orbit of it, but I didn't know the specifics on it, which makes sense, I guess, relative to the sun. So that's cool. I mean, this is just blowing my mind, though. His thought process. I mean, I've heard his name, and I know obviously Albert Einstein is so renowned, but I guess growing up, I didn't really know why so much. Like, I knew he had these theories and he was very impactful on the principles of science, but I didn't understand the degree to which he would have been influential to all of humanity. Yeah. Because he thought so much differently than everybody else. It's pretty crazy. I mean, I can't think of anybody today in our modern world that is similar to the way he's approaching physics.
Yeah. What do you mean? Like, that's coming up with like,
well, you would have
groundbreaking.
You would have like quantum physics, I guess, would be the next thing coming into play today. Yeah. And how, I don't know anything about that, but
I know a little bit, but not a lot. I read a book about it actually.
But I don't know any exceptional minds, quote unquote, that are really popular, because I think he became culturally significant as well, like pop culture. He became an icon of pop culture because he was so groundbreaking.
Yeah.
And I can't think of anybody like that today that is, I mean, I guess technology wise.
I was just about to say, like these days, like I feel like the equivalent of that is people coming up with like groundbreaking,
Technology,
like
yeah.
you know, like next level AI and coding and all of that kind
Robotics
of stuff.
and
Algorithms,
space travel
like
that we just saw with the
SpaceX,
with the chopstick arms with SpaceX. Anyways, let's continue. Finish this one up.
The only person in the world who realized that the universe actually works this way. But many skeptics still remained. Many scientists still had doubts about Einstein's theory. But the most foolproof confirmation of his theory came 4 years after he published it. That's when a team led by English astronomer Arthur Eddington in 1919 photographed stars near the sun during a total solar eclipse. If Einstein was right, then the position of the stars near the sun would appear different than their predicted locations based on where they should be as seen at night. This would happen because as light passed near the sun, it should be bent by the curvature of space due to gravity. And that's exactly what he found, confirming that the theory was correct. And this is the moment that Einstein became a celebrity. You might ask, okay, I get it. I get space curvature, but it's called space-time. How does time enter into the picture? Why is this not just a distortion of space, but also of time? This is where Einstein's first...
That's so
I totally
crazy.
forgot that was even a part of this because he'd gone like so far down this rabbit hole.
Yeah, I'm thinking like space and light, and I was like, oh yeah, I've got it covered.
No,
But no,
totally forgot
hold
about the
on,
time
'cause
portion.
How can you curve space without curving time at the same time? Wild.
It's not just a distortion of space, but also of time. This is where Einstein's first theory, special relativity, comes in. The essential presumption in special relativity is that light always moves at the same speed regardless of perspective or reference frame. This means that light will have the same speed in an accelerating reference frame as it will in a resting reference frame. If this is the case, then it means that the speed of light in the presence of gravity will be the same as its speed in empty space. Speed equals distance over time, s equals d over t. But since the distance traveled by the beam of light in a gravitational field is longer due to the curvature of space, in order for the speed of light to remain constant, time itself must pass slower in the gravitational field relative to time in empty space. In other words, time increases proportionately with the curvature of space near the gravitational field compared to empty space to keep the speed of light constant in both reference frames. This is why time is considered distorted by gravity along with space. It is really just part of the same fabric called space-time. This has some massive implications. It implies that the observer experiencing no gravity at all sees the clock in a gravitational field running slower. This means that the clocks on Earth are slightly slower than the clocks on the International Space Station. This effect has been confirmed by many experiments and is taken into account in order to keep the clocks of the GPS satellites in sync with the clocks on Earth. Otherwise, your GPS apps like Google Maps would give you inaccurate locations. Now, you should know that although general relativity is an astounding achievement by one of the greatest scientists of all time, it does not answer everything. Questions remain. Although it tells us how gravity works, it doesn't tell us what gravity exactly is. Why do massive objects distort space-time? What is the underlying connection between mass and space-time? It also predicts regions of space where space-time can get so distorted that nothing escapes, including light. This is called a black hole. But it shows that within the black hole lies something that seems impossible. And that is a mass concentrated to an infinitely small point with infinite density. This is called a singularity and is theorized to exist within the black hole. General relativity fails to work at the singularity. But infinities like this in science usually indicate some sort of incompleteness of theories rather than things that actually exist. To figure out what happens at these really small scales, we need our old friend quantum mechanics. But alas, the equations of quantum mechanics make no sense in terms of singularities or in terms of general relativity. So for now, the two theories remain incompatible. If we can bring these two theories together and truly understand how gravity behaves at the tiniest scales, we may answer the question of what gravity actually is. we'll need a new theory to figure this one out. And that theory is called quantum gravity. I'd like to thank my generous supporters on Patreon and YouTube. If you enjoy my videos, consider joining them. Or check out some of our other videos. I will see you in the next video, my friend.
Well, he did a good job.
I can't even imagine trying to comprehend gravity on a quantum level.
Yeah, well, I mean, I had trouble quantifying that video.
Same.
I guess that explains the idea of a black hole potentially being able to provide time travel. That's the theory, I think, that because we just talked about space and time and that all that changes inside of a black hole, that
eats you.
Huh?
It also eats you.
Well, we don't know that. We don't know what happens, basically, because nobody's ever gone into a black hole and come out of it, right? So I'm not an expert. I'm just basically referring what I remember hearing at some point or another, that black holes could be somewhat indicative of time travel to an extent.
Yeah.
But that's wild, right? That part that we talked about, whether you're in outer space, how that will change the reference of time. And
that makes sense, though, about the whole like time needing to be slower, because technically if you have the two different variations of the path that light's traveling, if one is the shortest distance, that means that you're going to get there faster, so that it needs to outweigh how long it's going to take for one to get there to keep it even.
Yeah, that's what he explained there. But it does, like he was saying, also leave so many questions unanswered about what's going on in the universe, and makes me really think like we don't know anything.
Yes.
I think also I remembered hearing something about, I'm going to get this wrong 100%, but you guys will know what I'm talking about, hopefully. They were testing that one, I think it was an electron, was in two places at the same time. So it kind of had thrown off a bunch of theories when they did this test because it wasn't supposed to be possible. Something to do with that. And everything in terms of, I think, the physics that we had understood. I think
you might be talking about like certain quantum physics things. And there's two different separate theories where they used to think that, I can't remember if it was a proton or an electron or what. I read about this in the book that I read about quantum physics, and how they used to think that one was only in one spot per time at a time, and now it's actually that like it's bouncing around, like it can be in two places at one time. It's all around us at all times.
I think, yeah, it's something like that.
I did a really bad job of explaining that,
but I think I
read about it.
I think it was even different. I think it was even beyond what you're saying. Is that like they thought things were moving initially, but now they realize, oh no, they're at two spots at the same time, which shouldn't be possible, because if you're at one place in space and time, then you can't be another place. Something.
Yeah.
I don't know. Anyways, I slaughtered it. But you know what I'm saying. You can hit the comments down below. I found this really cool, really informative. Definitely know more about general relativity now than I did before I watched this video.
I knew nothing going into this.
That's kudos to, well, you knew more about physics than I thought you did. And this guy did a great job here, for sure. Gonna see if he's got other stuff on the channel to check out. So let us know what you guys think of this video. Hit that like button if you enjoyed it. Let us know if there's other things you want us to check out. We appreciate all your support. Hit the subscribe button. Have a great day. We'll see you on the next one.
Thanks for watching.